Okay, so I'm going to tell you a little bit about our fairly small project on CyanoHABs. So first, what is a CyanoHAB? It's a harmful algal bloom that's produced by cyanobacteria, which are actually sometimes called blue-green algae, but they're actually a bacteria. So when we say CyanoHAB, we're actually kind of screwing up there because it's not really an algal bloom. But cyanobacteria they're bacteria, and they can do photosynthesis, so they can feed themselves. Amongst bacteria, these are a group that have the potential to make a huge number of secondary metabolites or natural products. And some of those compounds can be toxic, tumor-promoting, immune suppressant, skin irritant compounds. They can have lots of bad properties. But they have I don't want to give them a totally bad name because on the other hand, there's a compound, for example, largazole, which was found by Valerie Paul's group and Hendrik Lusch at University of Florida, which is going to maybe revolutionize how we can treat cancer. So they have good sides and bad sides, but we were really focusing kind of on maybe the bad side and monitoring some of those things. So when they bloom, they can put out toxic compounds. And the picture you see here was taken by Marilyn Maswell in the southern part of the Indian River Lagoon. It was kind of what prompted us to put in this proposal. And when they were dumping all the Lake Okeechobee out and it pretty much turned to a freshwater environment, this freshwater bacterium, or cyanobacteria, grew and made the microcystins, which you can see here. And what's bad about the microcystins is that they are very potent hepatotoxins. And if cattle and things, this is usually in ponds in the Midwest, and if they eat this, their livers pretty much dissolve and the animals will die. So when this happened in the Indian River Lagoon, it was really a very bad thing. So there are other kinds of cyanobacteria, and I call them Lingbia here, but some of these are now being given new names, or Morea and other things. But this one here, we have mats that look like this, but this is actually a freshwater one that can actually flow into estuary systems. And so we were interested to see if maybe some of the mats we saw were this one. And it makes saxitoxin, and some of you may have heard of paralytic shellfish poisoning. So if you eat bad oysters, you get this dread, awful disease. And that's caused by saxitoxin, which is produced, in fact, by this freshwater one. And then there's a plesiotoxin and the dibromoplesiatoxins, which are also made by Lingbias. And they are known as tumor promoters and are implicated in tumors in turtles in both Hawaii and Australia. And then the microcolons are ones that we've worked on, which are typically on reef habitats, but we had some inkling that maybe there were microcolons present in the river, and they're very potent immune suppressants. So down at a nanomole of material per liter can cause an immune suppression. So we wanted to see if any of these were present. So you've all seen this map before, and we were really, when we put this in, we didn't really have great collection capabilities, so Dennis's group was very kind and actually did a lot of the collections for us. So at his sites, he would collect the samples if they saw floating mats, and they also found some benthic samples, which they brought back to us, and then we would analyze those. And the goal really was, since they're doing all this water quality monitoring and on the seagrass health, if we could factor back in that water quality data with what might be causing toxic blooms, then maybe we'd have more information for the Indian River Lagoon Observatory, just another data set. And then maybe it would factor back into the dolphin health and, of course, to human health. So the methods were primarily samples were collected in spring and summer of 2012. The samples are freeze-dried, then they're extracted, and then were analyzed by LCMS, and we use MSMS. And then we actually matched the compounds to the molecular weights that we see and what we would expect for known compounds. Oops. And so this is examples, and I know you really can't see this from the back, so sorry about that. But these are examples of LCMS traces. And the ones that we really look at are what's called the total ion current, which is here at the top. And wherever you see a little peak goes up and it has a number above it, that's actually a pretty high, a compound that's present in high amounts. And so these are from floating mats, and almost all the floating mats look like this. And then this was the benthic sample that came from the Torpy Road area. There was a big bloom there. Oh, and I should say that down in the bottom, these are what are called extracted ion currents at different molecular weight ranges. So you see ions that aren't very common, but that you can actually then still see that maybe that minor metabolite is present. And so some of the compounds that were detected, almost every floating mat, I think there's just a couple that I wrote 100%, but it's probably like 99.5, had this compound was called malingalide. And malingalide is a quorum sensing inhibitor, so it actually, quorum sensing is where bacteria start to work together as not a single cell organism, but as a multi-cell organism. And this compound can block that interaction. And what that might have to do in the marine environment or how it's controlling these mats is still to be, I think, determined. And I think people at Smithsonian are working on that. We also saw compounds that were very pretty cytotoxic compounds, so lingbiabellin and malingamides we think are present in at least some of those. And then what I thought was most interesting was we really did in this torpy road benthic sample, we found microcolon A. And it is, once again, this very cytotoxic compound. And what would still need to be determined is whether any of these can translate up into the food chain in any way. But this was kind of just a preliminary study, what were we seeing, and what kinds of compounds are present. Now, a new direction that we've just started, and this is with some prompting from Brian LaPointe, who is very interested in a compound called BMAA, which is beta-methylamino L-alanine. And it's an amino acid that's produced by almost all cyanobacteria. And it's known to be neurotoxic. And it's actually been implicated in, amyotrophic lateral sclerosis, which is ALS, or Lou Gehrig's disease, which, if you're familiar with that, it's a very, you die from that pretty rapidly. And also with some Parkinson's dementia complex in people in Guam who they think get this into their diet from cyanobacteria that are in some cichlids that they eat. But anyways, it's also, University of Miami has also shown that there seems to be clusters of people who maybe are eating certain seafood that have ALS like Alzheimer's disease dementia, and that it could be tied back to BMAA, and they've actually analyzed the brains and find large amounts of BMAA, which is pretty scary. So there's some thought that maybe there's some clusters like that happening here in the Indian River Lagoon, and so maybe NSF is interested in funding this. So Brian asked whether we could try to set up an assay for BMAA. So there's problems with BMAA, and in fact, this is part of the controversy of whether it is really causative for this condition. It has a small molecular weight. There's no UV absorbance we can see. There's all these other compounds that can actually cause interference, of which one of them, DAB, actually is also a very potent neurotoxin. But when you're looking for this compound, some of these others may show up and interfere in your assay. So what we've been doing is just a little bit of, we did a very simplistic approach first. Could we buy DAB and BMAA and actually do a separation? So this actually shows an HPLC separation. And they are separating, but that's not good enough for quantitation and to really be able to say unequivocally that it's there. So we're actually using this method that was just published in 2012. We're just starting this, where you take the compounds and you derivatize them with something called a beta-carboline. And then you get a derivative that when you do LCMS, it's very different. This one will give ions that are 258, and this is 188. So you can clearly distinguish these things. And so this is the method that we're currently setting up in the lab, and that's going on. One of the interesting things is there haven't really been large blooms of cyanobacteria. We've gotten samples, and Dennis has found them a few times and brought them back to us, and we've gone out and done a little bit of collection. But there really haven't been these big blooms since we wrote this proposal. Although right now they're dumping Lake Okeechobee, I think, so we don't know what's going to happen. And so we still have some funding left, and we'll certainly be monitoring that. There is a large bloom that happens every year, pretty much every year, that's up at the Fort Pierce Inlet near the Little Gym area. And we didn't particularly monitor that because the Smithsonian has an excellent long-term monitoring program for that. But we did get some samples there, and in fact, they have these malingalides that we saw in the floating mats, and there's some question about whether there's a relationship between where all these floating mats are coming from. Once again, the floating mats that we analyzed all had malingalide as the major compound. We saw microcolon A in this benthic one, and we don't really know whether that can go up. I'm almost out of time. And we still have a few floating mats that had unusual compounds we haven't identified yet, and we're working on that, and we're setting up for BMAA. And if I can make it go. We thank Dennis and Kristen for doing all the collections for us, and Valerie Paul for discussions about what cyanobacteria they're working on and what they're seeing in the Indian River Lagoon. And I believe we're funded by Protect Wild Dolphins. And we'll keep you posted. So, did I stay on time?